Welcome to another example on related rates. So here's our problem. We have a man which is 2 meters tall. So here's our man. And he's walking away from a street light. So here's our street light. Just one of those. Street light looks nice. Street light. So there's the ground. Man's walking away. He's 2 meters. The street light is 5 meters, maybe not quite to scale. That's okay. His speed is 1 meter per second, and we were asked how fast is the length of his shadow increasing when he is 10 meters from the light. So presumably it's night, and the light is what's causing his shadow. So the shadow would kind of be in line with, that should be a straight line, with his head and the street light, right? So his shadow is here, kind of created by forming a line from the light right over his head down to the ground, and his length from the street light is right here. So let's give these letters. X is his distance from the light, and y is the length of his shadow. So, okay, so what do we know? We know dx dt. We know how fast his distance is changing from the post, right? It's changing at a rate of 1 meter per second. What don't we know? We don't know how fast his shadow is growing, or the length is increasing with respect to time, so that's our unknown. And we're told the instant we're looking for it is when x equals 10 meters. So that's our instant that we're looking for it at. So now we need an equation which relates x and y. So, one assumption we're going to have to make is that sort of the man's standing straight up and the lamppost, even though it didn't draw it straight up, we'll assume that it is. So what you got here, you've got two similar triangles, right? You've got this triangle, which is similar to this triangle because they both have right angles, and they both share this angle here. So two angles that are the same means the third one is, so all the angles are the same. So the triangles are similar. So, now what do you know about similar triangles? I know they have proportional sides, so similar triangles means proportional sides. So now let's set up our proportions. So our proportion would be, 5, this side is proportional to this side, or corresponds, right? This side corresponds with this side, so 5 over 2 should be proportional with, let's say, this side corresponds with this side. So that would be x plus y corresponds with y. So these should be proportional, hence equal. The ratios are equal. So now we need to solve this. We need to there we have a relationship between x and y. So we need to get dx dt and dy dt in here. So, based on the previous examples, you might say, okay, differentiate both sides with respect to t. But if I differentiate this with respect to t, I'm going to have to use a quotient rule, and I do not want to use the quotient rule. So here's a suggestion. Simplify first. So if I multiply both sides by y, I'd have 5y and both sides by 2. Sometimes you call that cross multiplying. I don't want to get in trouble. Some people don't like that. They think it's a sort of a bad word. But it tells us what we're doing. So I don't hate it, but it's not really what you're doing. And then we'll just expand there. And then look, I can group the y's. So subtract 2y from both sides. And we'll get 3y. So now this is a way better relationship between x and y. Way easier than this. That would have been difficult, to differentiate, and this is going to be easy to differentiate. So now I'll differentiate both sides with respect to t. So the derivative of 3y with respect to t would be 3 dy dt, so remember, sort of implicit, and 2 dx dt. So now remember, what are we looking for? We were told dx dt is 1. So 2 times 1, and then dy dt is what we're looking for. So we'll leave that. And if you solve for dy dt, divide both sides by 3. 2 divided by 3, and then I believe the units were meters per second. So 2 over 3, and then again, might be useful, 2.6, and if you round that, 7. Oh no, not repeating, 2.67 meters per second. So y is changing in a rate of, what was it, 0.67? 0.67, or 2/3 meters per second. So, okay, that's good. That's how fast his shadow is increasing. One point, remember when we said his shadow is when he is 10 meters from the light? Where did we use this 10? And the answer would be, well, we didn't, right? If you remember, previous examples, normally when you differentiate, you end up with like the rates, but then there's also like an x in there, and then you have to sub, the instant in there. But in this example, there were no x's. When we differentiated, there was no x, there was no y, it was just the rates. So what does that tell you? Well, it tells you that the rate does not change no matter where he is. So it's a constant rate, this dy dt. No matter where he is, the shadow is increasing at a rate of 0.67 meters per second. Which, if you think about it, kind of makes sense.